Welcome back, my dear students. In the last part of the video, we have discussed about a condensation polymerization of nylon 6,6 and nylon 6 and Decron. I hope you have not watched the video. I will provide a link over here. You can watch it. Now we are going with another type of a condensation polymerization, that is a phenol formaldehyde polymer and melamine polymers in this video. And apart from this, we are going to also discuss about rubber. What is natural rubber and what is synthetic rubber, and after the case about phenol formaldehyde polymer. I begin with the word phenol formaldehyde polymers. So phenol formaldehyde polymer, it is in a two way. It is prepared first to the preparation of novolac, which is a linear, and that novolac will undergo extensive cross-linking and forms a Bakelite. So here two parts are very important. One is Bakelite, another one is a novolac. So let us first discuss the preparation of a novolac. Here, as it is told, first the monomer used is a phenol, another one is a formaldehyde. Formaldehyde is a one carbon atom aldehyde, and you know what is the formula for phenols. In your theory class of the content, you might have alcohols, phenols, ethers lesson. You might have studied about this the word phenol. So phenol is the benzene with OH group attached. Will react with formaldehyde. Formaldehyde is a H C double bond OH, or I can write directly CH2O. Yeah, I can write directly CH2O. I can write. So we'll wipe out this one, and it is very easy for you people to understand. CH2O. Remember, but CH2O is nothing but HC double bond OH. So I write a CH2O. So here what will happen? So as usual, you know, here all the way hydrogen will be there, and here also hydrogen will be there. Why I am writing it ortho, para and ortho product is because OH group is a ring activating group. So it will direct incoming electrophile only towards either ortho or para or ortho position. So therefore you should just add one hydrogen here and you get the product. It's almost like OH as it is here, students, and you get at the terminal position at ortho you get CH2OH. Just to add one hydrogen, or you may get a different of the product, series of the product, three different product you get over here, but out of which only one is important for us, that I will proceed further with that one only. So you have a CH2OH again at ortho position, and a CH2OH at para position, and again you may have CH2OH here, or you may have a CH2OH at the down at para position, or you can have it at again here CH2OH. But for our study, I think this part is very important, because this is undergoing extensive cross-linking. We take almost n molecules of the same molecule here. OH, and I have a CH2OH, and here for my reference, here I write one hydrogen. This will undergo a polymerization in presence of an acid or a base. I take OH plus. Here you have to observe. So this OH and this H will undergo elimination like water. H2O eliminates. So you just have to form the series of the product. That series of the product will be there. At the terminal, what will be there? CH2. The chain continues, students. I'm going to write over that. And to that again, as usual, benzene ring. On the head of benzene ring, we have a OH, then connected with the CH2, then connected with the benzene. So unable to draw a right structure of the benzene. Please forgive me, because this tab is not allowing me to write properly. So I hope you adjust with the benzene ring. So see this. So continuously a benzene with the CH2 group are attached. See, this is a linear chain, N molecules. So this linear chain is extensively called as novolac. So this novolac, the major use of this, it is used in paints. The novolac is major used, that is used in paints. And remember, the same novolac on heating with a formaldehyde again undergoes extensive cross-linking to form an infusible solid mass, which is we almost call it as what? Bakelite. And this bakelite is used in making combs, okay, phonographic records, electrical switches, and handles of various utensils. See, that is also very important, the uses of your bakelite. Means whatever the novolac we got, the same novolac, whatever here we have written, I think easily you can notice down. This novolac undergoes extensive cross-linking. Extensive cross-linking means, see here how I write the structure of your bakelite. I think a novolac everybody can write without any problem, much problem over novolac everybody can write. As usual, students, here benzene with OH, and left side what is there? CH2, and this chain going to continue, that is secondary part. And here I have a CH2, again OH, and again CH2, and again OH. I think this partial structure of a novolac, I think everybody can write without a problem. Everybody can write this. So what you all need to do is to write the bakelite structure. Whatever the same structure I have written over here, the same structure whatever I have written, exactly reverse down you have to write. Means down I am writing wherever benzene is there. See, I am writing the same benzene. Now down here OH group will come. And here as usual at this position we have a CH2 attached. Same. I am not changing anything. Same structure down I am writing. So here also CH2 is there. And again what came? Benzene ring came. And to the benzene ring what is there, students? OH is attached. Again at this position what is there? Chain continues to be with the CH2. And again here comes our benzene ring with OH, that is a phenol. And here also CH2 at the end. So as usual this square bracket going to continue. You all need to do is connect each benzene ring by CH2 group. That's it. Here CH2 connected. Here CH2 connected. Here also CH2. And this is what we call extensive cross-linking. And this structure, I think we call it as a bakelite and infusible mass. It is used in making combs. See, it is used in making combs and electrical switches. Okay, it is also used in making phonographic plates, electrical cords, so various utensils. These all are the major application of the bakelite. So I think easily you can draw with the video is helpful you people to remember the partial structure of a bakelite, which is quite not important, but novolac they may ask you, right, the partial structure of a novolac. So after this we are going with the next polymers in the same content, that is we call it as melamine formaldehyde polymer. We are discussing melamine and formaldehyde polymer. This is a different type of a polymer again, melamine formaldehyde polymer. So this is also another important 2-mark question that can be asked to answer. So how this is prepared? Right now I am drawing the structure of a melamine. Almost benzene ring you have to draw, in which each carbon atom should be replaced by nitrogen. See, I think like this way everybody can draw this. Almost like a benzene. Okay, double bond will be as usual present here and here and here. And remaining 3 carbons should be replaced by this nitrogen atom. And here we have a NH2 group. At alternative position we have a NH2 group. Here also I am drawing NH2 group. So this is the structure of melamine, and formaldehyde you already know. I think I can write CH2O. So what will happen if you make a reaction over polymerize this one? Condensation, polymerization, one hydrogen, you can add O to the oxygen. So what does it become then? Same structure I am drawing, students. So N, and here one N. All are connected by alternative double bonds. So left side NH2, no change, drawing it. Here also NH2, no change. But this NH2 loses a hydrogen, no? Therefore it becomes NH, and that is connected to CH2OH. So this is a resin intermediate. So the name of this molecule, whatever that is formed over here, I think you can note down it to be resin intermediate. What we call resin intermediate. So this will lose water, that is undergoes a polymerization and lose water. From where water will be lost? H3O plus will be lost actually. So here one hydrogen, here another hydrogen, and here OH, all the way lost. And structure I am writing down here. I think you can notice the same structure. Here I am writing, there is no space, so that's why I am writing over here, so that easily we can visible. N, as usual. Okay, no change. Double bond inside the ring, melamine ring, will not change. So left side, what is left out? Hydrogen goes, then only NH left. Down, same NH left. Right side, NH, CH2 left, because OH goes. OH goes, therefore N only CH2 left out. So chain seems to be continued. This is the structure of melamine polymer. Melamine polymer. So melamine polymer is used in making unbreakable crockery. Remember, it is used in making unbreakable crockery. Always remember, it is used in making unbreakable crockery. I think this is all about the phenol formaldehyde and melamine polymer. So now we are going with another next different type of polymer. We call it as a natural rubber. A lot of question that has been asked in the board examination of our Karnataka state regarding the natural rubber. See, natural rubber is a polymer and possesses high elastic property. That is very important. See, it is highly elastic in nature. It is also termed as elastomer and has a variety of uses. It is used in manufactured from the rubber latex, which is almost a colloidal dispersion of rubber in water. I think in surface chemistry you might have studied about the word colloids. This latex is obtained from the bark of a rubber tree that is found in India, Sri Lanka, Indonesia, Malaysia and South America. See, natural rubber may be considered as a linear polymer of isoprene. This is very important point to be noted here. I write the word, a linear polymer of isoprene. Suddenly if I tell the word isoprene, you may not understand, but isoprene has a IUPAC nomenclature like 2-methyl 1,3 butadiene. 2-methyl 1,3 butadiene. So I'll just wipe out this part. It is not clearly written. So now I think I can easily write a linear polymer of isoprene, which is called as isoprene. What is called IUPAC nomenclature of isoprene? That is a butadiene. Buta means a 4 carbon atom will be there, 2 double bonds are there, one at first position, another at third position, double bond will come, and at second position methyl group will come. So this isoprene is a monomer of natural rubber, and this isoprene even also called as 1,4 polyisoprene. cis 1,4 polyisoprene. Now I'm writing that partial structure of that molecule here on the board. On the screen I'm writing CH2 double bond C, CH double bond CH2. See, note down this. I think easily you can tell this is a 1,3 butadiene because this is carbon 1, carbon 2, carbon 3, carbon 4. At first carbon atom and third carbon atom double bond starts. That's why it is buta 1,3 diene. And at second position we have CH3 group, methyl group. See this. So this is the structure of a partial structure of the word isoprene, which is commonly called as a 2-methyl 1,3 butadiene, which is the natural monomer of a natural rubber. So this isoprene, see, next the natural rubber is vulcanized. Charles Goodyear has synthesized it for the first ever time. What do you mean by vulcanization? See, natural rubber is very soft, and I show high temperature and brittle at a low temperature. It becomes very soft at high temperature and become brittle, almost breakable at low temperature. Almost high temperature means above 335 Kelvin it becomes very hard, and almost below 283 Kelvin it becomes very brittle, and shows high water absorption capacity, and it is soluble in non-polar solvents. And these physical property, in order to reduce or in order to control from these physical properties, the sulfur, calculated amount of sulfur is added to improve upon the process of consist of heating a mixture of raw rubber with the sulfur and an appropriate additive at a temperature of 373 to 415 Kelvin. This process is called as vulcanization. See, means whatever we take is a natural rubber, and this natural rubber is mixed with sulfur, calculated amount of sulfur, almost at a temperature of around 373 to 450 Kelvin, 373 to 415 Kelvin. So what will happen? The brittle nature becoming brittle at the low temperature or becoming soft at high temperature and showing high absorption, water absorption capacity will be reduced. And this rubber now mixed with sulfur, we also call it as a vulcanized rubber. We also call it as what? Vulcanized rubber. That is whatever in the market we are getting, that is vulcanized rubber only. And what will happen here? After vulcanization, remember 5% of sulfur is used as a cross-linking agent. And the probable structure will be, I'll show as between, all double bonds will be removed. In place of double bond, there comes the sulfur. So means as usual, this CH2 will be there. I think you can have a reference of this structure over here. Same structure I'm drawing down here, same structure. Wherever double bond comes, there sulfur comes, because there only it is added. Okay, what is there? C, CH3, single bond CH, single bond CH2. Double bond will go, because the double bond, where double bonds are there, I think there we add a sulfur. So here double bond was there at this carbon, there sulfur will come. And at this carbon also there was a double bond, here also sulfur comes. And this is again connected to a same structure down below you can write. Means almost I write here CH2, and here comes C, here comes CH, here comes CH2. At the bottom, as usual, what will be present, student? CH3. So this is the partial structure of a vulcanized rubber. Partial structure of vulcanized rubber. So this is how rubber is made into vulcanization. So upon vulcanization, all these property will be increased. So I hope there is no difficulty with the vulcanization of a rubber. Then we are going with a synthetic rubber. See why? Because synthetic rubber is any vulcanized rubber. Remember, any vulcanized rubber polymer, synthetic rubber. Here I write below. Synthetic rubber. For synthetic rubber, we are using the monomer as a chloroprene. Chloroprene is a monomer. Chloroprene, which is commonly called as a 2-chloro 1,3 butadiene. Very simple. Already you know in natural rubber 2 methyl 1 comma 3 butadiene was present. Here I write 2 chloro 1 comma 3 butadiene will be the monomer that is used in preparation of synthetic rubber. So I take n molecules of chloroprene. It is CH2 CCl CH double bond CH2 n molecules. This will be polymerized. When it is polymerized, just here a double bond comes now. So this double bond shifted here. This will go at the terminal position. So means all double bond will become single bond and single bond will become double bond. So how the polymerized structure will be there? I'm writing here CH2. Now it becomes single bond Cl. Here single bond was present, that becomes double bond CH. Single bond CH2. The chain continues to be n molecule. So this is called as a neoprene. This is called as a neoprene. And superior resistant to the vegetable and mineral oils, this neoprene, that is synthetic rubber, and it is used in manufacture of conveyor belts, gaskets and hoses. So these all are the uses of a synthetic rubber. Now we are going with another type of polymerization. So that we'll discuss in the next part of the video, that is copolymerization and biodegradable polymers. So in the next part of the video we are going to discuss about copolymerization, where we study Bohnian and Bohnius preparation, butadiene and styrene, and butadiene and acrylonitrile, as well as for biodegradable polymer, that is we have a polybeta hydroxy butyrate, co-beta hydroxyvalorate, which is called as a PHBV. So in the next part of the video we'll be discussing that content also. So thank you for watching, students. Have a good day. Thank you very much.